Hello everybody. In today's session, we see the behavior of resistor, inductor, capacitors in AC circuits. See here, any electrical network can be a combination of resistors, inductor, capacitor, or resistor, inductor, or resistor and capacitor. If the network has all resistors, then I call the network as a resistive network. If a combination of resistor and inductor is there in the network, we call the network as an RL network. If the network has resistor and capacitors, then I call the network as an RC network. If a network has all three components, resistor, inductor and capacitor, it becomes an RLC network. It is possible to connect these elements either in series or parallel or series parallel or parallel series. So, based on their interconnection, I get different kinds of circuits. Today we see here the behavior of resistor first. The resistors R is connected across the terminals of an AC voltage source in the slide what I have shown here. Okay. The A is the voltage source, R is a resistance. So, this will give you a current I flowing to the resistance. Now, the terminal voltage applied or the voltage applied across the resistor R will be V. Suppose that the AC voltage is a sine wave with an instantaneous value of the voltage equals to V of t is equals to V maximum sin omega t. It is a sinusoidally alternating quantity with a magnitude of Vm. Now, in this network, if you see the current at any instant in the network can be obtained by applying Ohm's law to the resistance. According to Ohm's law, we have the current I of t in the network at any instant is equals to the voltage V of t divided by the resistance R. If I substitute the value of the voltage in this expression, I will be getting the current expression as Vm sin omega t divided by the value of R. Here resistance is constant. Therefore, I can also write this equation as Vm divided by R sin omega t, and I can write down this as Im sin omega t, where Im is the maximum value of the current given by the ratio Vm by R. Now, if you see the waveform here, the voltage and the current waveform, they are given here. The current waveform is represented by the dotted line. Okay. Now, if you see here in the waveform for the voltage and current, when the voltage is varying according to a sine curve with a period of 2 pi radians, the current is also following the sine curve like this. Okay. So, the first waveform is a voltage waveform V of t, the second one is the current waveform I of t. Now, as per this equation for the current I of t, if you substitute omega t is equal to 0 or t is equal to 0, I will be getting the voltage V of t is equals to Vm sin 0, therefore, it is 0, and I of t at the same instant is given by Im sin omega t, this is also 0. When at the instant when omega t is equal to pi by 2, you can have the voltage given by V of t is equals to Vm sin pi by 2. So, this is the maximum value of the voltage, and the current I of t is equals to Im sin pi by 2. I will be getting this as Im. So, from this relationship we can say that when the voltage is reaching a maximum value, the current also reaches the maximum value. When the voltage reaches a 0 value, the current also becomes a 0 value. So, this means that the two waveforms are in phase, or you can say the current in a resistor follows the voltage with a phase angle difference of 0 degrees. This can be represented by the phasor diagram drawn for the resistance. When I take the voltage as a reference, the current will be following the voltage. It is like this. Okay. First phasor is V, the voltage, second phasor is the current I. If I represent this diagram in the coordinate system, I will be getting this phasor diagram as like this. This is my reference axis. I have the voltage along the reference axis. When omega t is equal to 0, the current is also along the reference axis. That is why when these two vectors are rotated in the counterclockwise direction, any person standing at one particular point can observe that the voltage and current will be following each other, okay, for all instants throughout the rotation. That is why we say in a pure resistor the voltage and current are in phase. Now this is the waveform representation of voltage current relationship in a resistor, and this is the relationship between the voltage and current in a pure resistor in the form of a phasor diagram. Now if you take, I have given you the expression for the voltage applied across the resistor, and this is the current flowing through the resistor. Now if I calculate the power at any instant, I can take the value of the current at that instant and value of the voltage at that instant. Product of these two will give you the power at any instant as V of t multiplied by I of t. You can see V of t is given by Vm sin omega t, I of t is given by Im sin omega t. Therefore the product can be written as Vm Im sin square omega t. If you draw the waveform for the instantaneous power, for the positive half cycle, because the voltage and current both are positive, the power will be positive. So the power will be product of these two. Therefore I will be getting a power curve like this. This is your P of t. During the negative half cycle, the voltage and current both are negative. Therefore the product will be again positive. I will be getting a power curve this way. So if you see that in the pure resistor, power is unidirectional, and the simplified expression for the power, I can also write it as Vm Im, converting this sin square omega t as 1 minus cos 2 omega t divided by 2. So I can write this as Vm Im by 2 minus Vm Im by 2 into cos 2 omega t. The second term in this is a cosine function with a frequency of 2 omega. Okay. Now the average value of the power can be obtained by integrating this instantaneous power over the full period. Okay. When I integrate the second term over the full period, the integral of cos 2 omega t tends to 0. Therefore we are left out with only this first term, whereas I can write average power P is equals to Vm Im by 2. Writing this in terms of RMS value, Vm by root 2, Im divided by root 2, I can write this as V the RMS value multiplied by I the RMS value of the current. So the average power in a pure resistor is given by the product of RMS value of the voltage and RMS value of the current. So the average power on the waveform can be represented by average ordinate here, which is given by P average is equals to RMS value of the voltage multiplied by the RMS value of the current, like this. So we see this in a pure resistor, for a circuit in a pure resistor, the current is in phase with the voltage. Therefore the phase angle difference between the voltage and current is 0 degrees. So therefore I say the power factor for the pure resistor is cos 0, it is equals to 1. So this gives us the total power in a resistor circuit is Vi cos phi in an AC circuit. Phi is equal to 0, therefore, this is also will give us Vi. Yesterday's class I told you in that AC circuits, the product of V into I, which is the RMS value of the voltage and RMS value of the current, is called apparent power. Because for the pure resistor the power factor is 0, I say the apparent power and real power both are equal in the case of pure resistor. Now I will take an inductor. The inductor is made up of a coil or a conductor wound in the form of a coil, or we can also have a straight conductor with some inductance. Inductance is represented by L, the units are Henry. I am applying a sinusoidal voltage source. Say the source is A, the voltage of the source is V of t. So this causes a current of I of t to flow into the inductor. So the voltage what I am applying by connecting the source is V of t here. Now since I am applying a sinusoidal voltage source, the current what is flowing into the inductor is also sinusoidal. So because the sinusoidal current will have an time changing magnitude, the flux produced by the current in the coil also follows a sine curve. This flux linking with the coil having N turns and an inductance of L will give you flux linkages. Because that flux is changing, the change in the flux linkages will induce an EMF in the coil, that is as per the Faraday's law. Now the induced voltage in the inductor, if I represent it by a letter E of t, I can write this as L di by dt, dit of dt, okay, L di of t by dt. Now this L is an inductance. Now as per the Lenz's law, this induced voltage will oppose the supply voltage, therefore in a pure inductor I can write this E of t is equals to minus V of t, or the voltage V of t is equals to minus L di of t upon dt. Now let us consider that the current what is flowing to the inductor I of t is given by Im sin omega t. If I substitute this expression for current in the expression for the voltage, then I have V of t is equals to minus L d by dt of Im sin omega t. So this I will be getting minus L, Im is a constant value, omega cos omega t. Okay, this is what I have shown here. I can also write this equation as omega L Im sin omega t plus 90 degrees. So the cos omega t in terms of sin can be written like this, okay, sin omega t. Of course I have a minus sign here, so if I remove the minus sign I can write it as omega L Im sin of omega t minus 90 degrees. We can write like this. So this says the induced voltage or the terminal voltage here what you have, okay, V of t, that is the voltage applied to the inductor, it is fine. I just made a mistake here, I will write it as 90 degrees here plus 90, or I will erase this second equation. So this says that the voltage across the inductor leads the current by 90 degrees. Why I am saying current leading means I have taken sin of omega t, Im sin omega t as the current expression. So this is giving us a voltage of V of t, which is equal to sin omega t plus 90. So that gives us the phasor diagram for the voltage and current relationship in the case of inductor as I, the voltage what you have here V of t or V you write. So this is what you have plus 90 degrees or pi by 2 degrees, okay, pi by 2 radians you can also call. When you see this E of t is equals to minus V of t, I have the E of t, the induced voltage what you have lagging behind the current by pi by 2. The terminal voltage is leading or the applied voltage is leading the current by pi by 2, okay, induced voltage is lagging behind the current by pi by 2. So this is the phasor diagram for a pure inductor. I can also represent this in the form of the waveforms. We can have like this. This is the current waveform what I am taking it as a reference. This is I of t with an instantaneous value of I of t. This is omega t. I have the voltage expression, voltage waveform. So this is my voltage waveform V of t. So along this I have the voltage as well as the current. Now when you take this equation, I can write omega V L, omega L Im as Vm, because this is the expression for the voltage. Current multiplied by omega L will give you the maximum value of the voltage. Vm sin omega t plus 90 degrees I can write this, okay. Vm sin omega t plus 90 will be the maximum value of the voltage. Vm is the maximum value, Im is the maximum value of the current. And again here if you try to write down the product of the voltage and current at any instant to compute the instantaneous power, we can have, if I substitute the expression for voltage and current, I have Vm sin omega t plus 90 multiplied by Im sin omega t here. This will give you Vm cos omega t, Im sin omega t. So this is Vm Im cos 2 omega t, sorry, sin 2 omega t, I am sorry, this is sin 2 omega t, okay. We get like this. Actually it is 2 sin 2 omega t, because I have just cos omega t and sin omega t. We have in the trigonometry the identity that 2 sin theta into cos theta, I can write it as sin 2 theta. So since I have sin theta and cos theta, I can write this is equal to 1 by 2 times sin 2 theta, this product, that is without this 2 I can write sin theta cos theta is equals to 1 upon 2 sin 2 theta. So based on this identity, the instantaneous power expression can be written as 1 by 2 Vm Im sin 2 omega t. Now if I show that as a waveform here, waveform way, I take this point where the current is 0, voltage is maximum, so the product will be 0, and at this point where that is omega t is equal to pi by 2, I have a maximum value of the current, but the voltage is 0, therefore the power, the product which is gives us the power, product of voltage and current is the power, that is also 0. So between these 2 points the power varies as per sine curve, okay, like this. And here when omega t is equal to pi, omega is equal to pi, from pi by 2 to plus pi, the current is decreasing but it is positive, the voltage is negative and it is increasing, therefore the product is again positive, positive, okay. One second, I did a mistake here. In the 0 to pi by 2, both current as well as the voltage are positive, therefore the power is positive. Between pi by 2 to pi, the current is positive, voltage is negative, therefore the product will be negative. It is following a sine curve. Between pi to 3 pi by 2, voltage as well as current both are negative, therefore the product will be positive, and between 3 pi by 2 to 2 pi, I have voltage as positive, current is negative, therefore the power is negative. Now you can see here, in a pure inductor, when the current and voltage completes one cycle, that is 0 to 2 pi radians, the power is completing 2 cycles. Okay. So this is the first cycle for the power, 0 to pi, pi to 2 pi is another cycle. So therefore we can say the power frequency of the power wave will be double that of the frequency of either voltage or current. Okay, either voltage or current. If you compare these two, I have here 2 omega t, therefore the instantaneous power will have a frequency of double that of the voltage or current. Now if you try to calculate the average value of the power either over a half period or a full period, you can see here the positive half cycle of the instantaneous power is exactly equal to the negative half cycle of the instantaneous power. Therefore the average value of the power over a half cycle of 0 to pi for the voltage or current or is equal to 0 here. So the positive average value and the negative average value cancels, so I get a 0 value, or in this cycle also I will be getting a 0 value. Therefore the total power consumed by the pure inductor will be 0, that is the average power consumed by the pure inductor will be 0. So this can be also proved by calculating the average value of the power within a limit of 1 upon 2 pi, okay, integral 0 to 2 pi p of t d omega t. So by this equation I will be calculating the average power, that is area under the power curve over a cycle divided by the length of the power cycle will give you the average power. Okay, 1 over 2 pi I have calculated for the full period of the voltage or current. Okay, so that is why I have taken the limit as 0 to 2 pi. So this gives you a value of 0 for a inductor. So this says when a pure inductor is there, it will not consume any average power. So this waveform here, it shows us 2 voltages and 1 current. The current is taken as reference, therefore when omega t is 0, the current is 0. The dotted line represents here the induced voltage in the inductor. This induced voltage opposes the applied voltage. Okay, when there is no resistance, these two are equal and opposite. Therefore as I am considering the pure inductor here, the dotted line when is inverted will give you the voltage applied. That is this thick line what you are showing here, this is the applied voltage across the inductor. So these are the phasor diagrams which I have already given. Okay, I is the reference line, induced EMF is lagging behind the voltage by pi by 2 or 90 degrees, the applied voltage is leading the current by 90 degrees. Now this is with respect to the current as reference. Suppose if I take the voltage as reference, I can draw the phasor diagram for the inductor as taking the voltage V as reference, the current will be lagging behind the voltage by 90 degrees. That is, in a pure inductor with voltage as reference, the current will lag behind the voltage by 90 degrees. I have a term called inductive reactance. In writing the expression for voltage V of t, I said the product omega L Im, it will give you the maximum value of Vm. Here if you just take the term Vm, if you take the term Vm, what I call it as the maximum value of the voltage across the inductor, it is given by Im into omega L. Now this, as per Ohm's law, voltage is equal to current multiplied by ohms. Okay. So therefore, as per this equation, omega L will have a unit of ohm. Okay. That is, unit for the product omega into L is ohm. And then this omega, it is the angular velocity, it is given by 2 pi f, where f is the frequency of the supply in cycles per second or hertz. Okay. Now see here, I can also write the maximum value of the current Im is equal to Vm divided by omega L. So voltage divided by something which has a dimension of resistance only can give you current. Okay. Therefore, I say omega L will have the same dimension as that of the resistance. Okay. But this quantity I call it as inductive reactance. Okay. Therefore, in an inductor, the ratio of voltage to current, that is Vm divided by Im, we can also write it as Vm divided by root 2 Im divided by root 2. There won't be any change in the ratio when I write like this. Okay. So this is equals to RMS value of the voltage to the RMS value of the current. Okay. This is equals to omega L, where omega L is called inductive reactance because it is due to the inductance of the circuit. Okay. And normally this inductive reactance is represented by a letter X. I put a suffix L here to say that it is because of the inductance. Okay. So this is 2 pi f L. So whenever the inductance is given in the AC circuits, you need to convert that into ohms by multiplying with the angular velocity omega or angular frequency omega in radians per second. Now this angular frequency omega will be related to the frequency in cycles per second by the equation 2 pi fl. If this is f is 50 hertz, then 2 pi into 50 will give you 314 radians per second. So omega becomes 314 radians per second. So XL is equal to 314 multiplied by the L value. If L is 0.5 millihenry, then I will be getting that 314 multiplied by 0.5 millihenry will be the inductive reactance of the circuit. Now I said you, taking the current as a phasor, current phasor as reference, the voltage phasor across the inductance is given by, see I just told you like this, in drawing the phasor diagram for the inductor, in the beginning I have taken current as a reference, and then the voltage V, it is leading the current by 90 degrees. Now if I write down the coordinate axis passing through the reference I, this is the real axis, and vertical axis passing through the voltage vector. Vertical axis in the case of complex mathematics, I call it as imaginary axis. It is imaginary axis, x axis is the real axis. So the voltage phasor is along the imaginary axis. Therefore, I write the voltage across the inductor VL, okay, this is the RMS value as magnitude, that is I write like this, J times I XL, where this I is the RMS value. Okay. Suppose if both the sides of this expression you divide by root 2, then I have Vm by root 2, this will be Im by root 2. So that will give you Vrms, Irms multiplied by omega L. So that case, because this gives you the voltage across the inductor, I call VL, which is equals to Vm by root 2 in this equation as the RMS value of the voltage across the inductor. This voltage, because it is along the positive vertical axis or the imaginary axis, I represent it as J times IXL. Okay. Now here J we call it as an operator. Okay, J is called as an operator. It has a value of 1 and a angle of 90 degrees. Any vector, okay, any vector, if you operate that vector on this letter J, the position of the vector will be changing by 90 degrees in the counterclockwise direction. Okay. Now what I want to say is, in this absence of J, okay, in the absence of J, because the current is reference axis, okay, current is along the real axis whose magnitude is I, angle is 0, XL is a pure number, therefore IXL will be the voltage drop with an angle same as that of the current. Now when I put this J, I am getting the voltage V along the imaginary axis. The J stands for imaginary term, okay, right. Now let us say this J is not there, then what happens? IXL will be along this reference line. When I put J, this IXL which is along the reference line will be now rotated by 90 degrees, therefore it comes to this position. So that is what, when you operate this IXL by J, without altering the magnitude, the position of the vector will be rotated by 90 degrees in the counterclockwise direction. Okay. So this slide tells you about the power and power factor in a pure inductor. Now in the pure inductor, you can see I have taken the current as a reference, therefore I have the current vector starting from the origin, okay. Now the voltage in the current vector, here actually the voltage is taken as a reference, so the current is represented by thick line here, okay. So that is, I am changing my phasor diagram taking current as reference. Here I have taken current as reference, therefore I am getting like this. So from the current reference I am getting the voltage reference. So what I should do to change the reference? The complete phasor diagram what you have, rotate this by counterclockwise direction by 90 degrees. Then what happens? The voltage vector will come like this, okay. The current vector will come down like this. This is the voltage across the inductor, this is the voltage current in the inductor I. So what I can say, when I am taking the voltage as reference, the current in the pure inductor lags behind the voltage by 90 degrees. That is what happening here, okay. See, now if you check the 0 value of the voltage and the 0 value of the current, there is a phase difference of 90 degrees between them, okay. This waveform what I have drawn, it is with respect to the voltage as a reference. Now you see here, as I told you, between 0 and 90 degrees the current is negative but the voltage is positive. Therefore I have the power as a -1, so it varies like this, okay. So wherever the voltage and current are positive, I have positive power, wherever the current is negative and voltage is positive, I have a negative power, like that, okay. See here, this is negative because the current is lagging behind. The phasor diagram what I have drawn on the board will represent a different way here, because there I have taken the current as a reference, okay. It is just inverse of this, okay. So either way you can represent the average power to compute the average power, either that waveform or this waveform can be used. Now in this you can see here the power is negative because the current is negative, voltage is positive, and in the next half cycle of the power is positive because the voltage and current both are positive. Now after 180 the current is positive but the voltage is negative, therefore the power is negative, and after 270 you can see the current and voltage both are negative, therefore the power is positive. Again here also the average value what you have for the power for the negative half cycle and the positive half cycle within 0 to 180 degrees they cancel each other, therefore I will be getting a 0 average value for one cycle for the power curve, okay. So this slide will tell you about the same thing what I just told, okay. Either the voltage or current will be 0 at 0 degrees, 90 degrees, 180, 270 or 360, therefore at this instance the power 2 is 0, okay. So the next line says between 0 and 90 the voltage is positive, current is negative, and between 180 and 270 the voltage is negative but the current is positive, therefore the power will be negative. because plus into minus is minus or minus into plus is minus. Okay. Between 90 and 180 degrees the power will be positive because both voltage and currents are negative, okay, between 90 and 180. So like that 90 and 180 actually both are positive, therefore the power is positive. And between 180 and 270 again the current power is negative. Between 270 and 360 both are negative, therefore power is positive. Okay. So if you see the power waveform, we can say the power varies sinusoidally, okay, whose average value over a complete cycle is 0. The power consumed by the pure inductive circuit is 0. The real power in pure inductive circuit is P is equal to VI cos theta. Theta is 90 degrees, so cos 90 is 0, therefore power is 0. That is, the real power is 0. Apparent power is still VI only. Apparent power is there. So power factor cos theta is equal to 0. Okay, cos theta is equal to 0 degrees, 0. Therefore, I will call it as 0 lagging power factor. Okay, pure inductors will have 0 lagging power factors. Now, what happens to all this power? What is given to the inductor? Apparent power, where it is going? Okay, when you have a real power, there will be another power called apparent power. Reactive power. Okay, it is the power consumed by reactor. Okay, reactor in the sense it is due to the property of inductance only. So that we see in the later slides, what is the real power and what is reactive power, the difference between the real power and reactive powers. When it comes to an AC circuit where we have a combination of resistor and inductor or resistor and capacitor, we can tell the difference between real power and reactive power. Okay. Now I will consider a pure capacitor. C is the capacitance, A is the voltage source. We are applying a voltage of V of t to the capacitor. So there is a current of I of t in the capacitor. The relationship between voltage and current in the case of a capacitor is I of t is equal to C times the derivative of the voltage dV of t by dt. Let us consider that we are giving a voltage of V of t is equals to Vm sin omega t for the capacitor. So if I differentiate this, I can write down the current expression as I is equal to I of t is equal to C times Vm omega cos omega t. Okay. Or we can also write it as omega c Vm cos omega t. Here Vm is the voltage. Therefore, I am writing an expression for current. We have a product of some parameter omega c multiplied by voltage. In electrical circuit, if I want to calculate the current, you need to divide the voltage by some parameter which has a dimension of resistance. Therefore, I will rewrite this as Vm divided by 1 upon omega c cos omega t. The cos omega t can be written as sin of omega t plus 90 degrees. We can write like this. Now because I have voltage divided by something, so that gives us a current, I will give Im for this term and then sin of omega t plus 90 degrees. If you see this equation, compare with that voltage at the instant when omega t is equal to 0, I have the voltage V of t is equal to Vm sin 0, that is equal to 0, whereas the current I of t is equals to Im sin of 0 plus 90. Therefore, I have sin 90 is 1, I get a maximum value for the current. Similarly, when omega t is equal to 90 degrees, I have the voltage V of t is equal to the maximum value and the current I of t is equals to Im sin of omega t, that is 90 plus 90, 180, sin 180 is 0, therefore I of t is equal to 0. Okay? If you just take these two values and try to write down the waveforms for voltage and current, taking the voltage as reference, I will be getting a sine curve for the voltage like this with a period of 360 degrees, half the period is 180, quarter period is 90 degrees, starting value is 0, I have a maximum value of Vm here. Okay. Along this axis I am taking the instantaneous voltage. On the same waveform for the same amount of period, if we try to write the current waveform, when omega t is equal to 0, voltage is 0, the current is maximum, Im sin omega t, and you see this is positive. Okay. So if I take the value of Im to be slightly lesser than the voltage, I have a maximum value. When the voltage is reaching maximum, by the time omega t changes from 0 to 90, the current is coming down to 0. So this is my current waveform. Okay. So this phase angle difference of 90 degrees between voltage and current will be there throughout the movement. So like this is my current waveform. Okay, this is current waveform, and the dotted one what I am representing is the current, thick line represents the voltage V of t and I of t. Okay, here in the waveform I have represented, the current waveform is not represented by dotted line, but it is also represented by thick line. You can make out this because I have just indicated the current and voltage expressions there. Okay. I have here the maximum value of the voltage is this, and the maximum value of the current, it is Im. Okay. Im is given by Vm upon 1 over omega c, or you can also write down this expression for the current Im. Okay. Now if you see the phasor diagram, I can also draw the phasor diagram taking the voltage as reference V, the RMS value of the voltage, I have the current I in the capacitor leading the voltage by 90 degrees. Why I say leading means in the expression for current I have a plus 90 here. Okay. So this plus sign says the current will in the capacitor leads the voltage by 90 degrees. Okay. So when I take V is equal to 0, magnitude of V, angle of 0 degrees, I can write down the current as current with a magnitude of I and an angle of 90 degrees. This is what we have, we represent the current as vectors. Instead of writing I at an angle 90, I can also write this as J I. The J stands for 1 at an angle of 90 degrees. Okay. Now I will just come to the term what I am using here, 1 over omega c. Since I have written this Im is equal to Vm divided by 1 over omega c, I can also write down this term as Im is equals to Vm divided by Xc, where that Xc we call it as capacitive reactance. Okay. So that Xc will be 1 over omega c. Okay. So if I write capacitive reactance as 1 by Xc, this has an expression of 2 pi f c. So the capacitive reactance is inversely proportional to the supply frequency f and is also inversely proportional to the capacitance value. Okay. So the ratio of voltage to current, okay, here I can also write this equation as Im multiplied by Xc is equal to Vm, or Xc is equal to Vm divided by Im. I can write down Xc is equals to Vm divided by root 2 upon Im divided by root 2. So, this gives us the RMS value of the voltage to the RMS value of the current. So, the ratio of RMS value of voltage to the RMS value of the current also gives us the capacitive reactance for the circuit. If you see the last line here, I say for purely capacitive circuit, the reactance varies inversely as the frequency and the current varies directly as the frequency. Why I am saying the current varies directly as the frequency means, in the expression for Im, what I have, Im is equals to omega c into Vm, omega is 2 pi f c, okay. So, you can see here with c, Vm, 2 pi, these are all constant, Im is directly proportional to the supply frequency f. Now, if I take the current phasor as a reference, now why I am asking you to take sometimes the voltage as a reference, sometimes as the current as a reference means, in the coming chapters you can know about when you have a combination of resistor, inductor, resistor, capacitor or all the three elements, you need to take a common vector as a reference, okay. Depending on the interconnection of the elements, sometimes I take the voltage as reference, for some circuits I will take the current as a reference, right. To directly tell you, in all the circuits where the elements are connected in series, I will be taking the current as a reference quantity, because all the elements when they are connected in series, they carry the same current. If in a circuit a resistor, inductor or resistor and capacitor, they are connected in parallel, they share the current, but they carry the same voltage across them. So, because of that, in parallel circuits we will be taking the voltage as reference. Therefore, I need to draw the phasor diagram for inductor and capacitor taking voltage as reference or current also as a reference. This is what I have drawn the phasor diagram for capacitor taking the voltage as reference. When I take the current as reference, again as I told you about the inductive circuit, this phasor diagram, if I rotate it in the clockwise direction by 90 degrees, I will be getting a phasor diagram like this. I, it is a reference, the voltage will be lagging behind by 90. So, the complete diagram will just rotate it by counterclockwise direction. So, here also I have the, because you can see here as per the second diagram, when you have the voltage lagging behind the current, because this is the negative imaginary axis, okay, the vertical axis what I have, this is my vertical axis, the voltage is along the negative vertical axis. Therefore, I will be using a letter minus j before the voltage. Now, in this slide here we are seeing the power relationship for voltage and current for the capacitor. As per the slide you can see here, between 0 and 90 you have the voltage and current both are positive, that is what you have here. So, therefore, the power is positive, and between 90 and 180 the voltage is positive but the current is negative, therefore, the power is negative. Again between 180 and 270 both are negative, therefore, the product what is have instantaneous power, that is positive, and between 270 and the remaining part of the cycle I have the current as positive, voltage is negative, therefore, the power is negative. Again here also if you calculate the average value for the entire cycle for the power, that is 0 to 180 degrees, I get a positive average value cancelled by negative average value, therefore, the total average value for power will be 0, which means that the capacitor circuits or pure capacitors will not consume any average power. So, the real power in a pure capacitive circuit is given as P is equal to Vi into cos theta. Here theta is 90 degrees again, therefore, power factor is also 0, because the current is leading the voltage, I say the power factor is leading, but the value will be 0. So, this slide will just give you a comparison of RLC behavior, that is resistor, inductor and capacitor behavior in AC circuits. I just compared the 5 properties for this each element. I have taken the current here, current in the resistance is V by R, inductance is V by omega L in the inductor. So, V by 2 pi FL. So, you can say the current in the inductor is inversely proportional to frequency and inversely proportional to the inductance also, whereas here the capacitance value in the capacitor, the current is directly proportional to frequency. Now, frequency dependency, if you say for the resistance, in the case of resistance, because the resistance is a pure constant and the voltage current relationship for the resistor is linear, that is any variations in the voltage, current also follows the same variation, we say the frequency dependence between voltage and current is not there, whereas in the case of inductance it is directly proportional. Okay. Why I am saying directly proportional means this inductive reactance, it is given by 2 pi FL. So, therefore, that L value, you can see here the last reactance value. So, that is what here it is inversely proportional. And power, if you take Vi cos phi, that is Vi is the real power in the case of resistor, that can be calculated by V square by R or I square R, where V is the RMS value. In the case of inductance, the average power will be 0 and also the capacitance is 0. The phase difference, if you take in a pure resistance, the phase difference is 0, but in inductance it is lagging by 90, and this 90-degree leading, right. So, reactance, it is just R, resistance only, but inductance I write JXL is equal to J times omega L, here I write minus JXC is equal to 1 over omega C. Therefore, the inductive reactance is always positive and the capacitive reactance is always negative. So, this you have to remember, so far you are studying the AC circuits. So, today class I just explained to you about the behavior of the basic electrical elements in the AC circuits, that is when I am applying a single phase AC supply to a resistor, inductor and capacitor. This slide what I am showing will completely describes the today's session. Thank you.